In this video, I'm going to find the general solution of the heat conduction equation, which is defined by the second partial derivative of u with respect to x is equals to 1 divided by c multiplied by the partial derivative of u with respect to t. The c there is a constant which is greater than 0. So we have that partial differential equation, and I'm going to solve it using the method of separation of variables. For the method of separation of variables, we assume a solution which is of the form u is equals to x of t multiplied by t of t. Here we are just emphasizing that the x is a function of x only and the t is a function of t only. That's why we have those x and t in lowercase in parentheses. But we can just write in short as x multiplied by t. So we have this u here. But in our differential equation, we have a second partial derivative of u with respect to x. So what you need to do is we need to differentiate this with respect to x. And when you do that, we get that the partial derivative of u with respect to x is equals to the derivative of x with respect to x multiplied by t. But this part here, the derivative of x with respect to x, we can write it in short as x prime so that our equation becomes x prime multiplied by t. To get the second derivative of u with respect to x, we differentiate this with respect to x for the second time so that we get the second partial derivative of u with respect to x is equals to x prime prime multiplied by t. In our equation, we also have the partial derivative of u with respect to t. So we differentiate this u with respect to t so that we get the partial derivative of u with respect to t is equals to x multiplied by t prime. We now go on and substitute these values into our equation here on these parts so that we have x prime prime t is equals to 1 over c multiplied by x multiplied by t prime. So that's the equation that we are having now. I can now put the functions x on one side, the functions t on one side, so that we have x prime prime divided by x is equals to 1 over c multiplied by t prime divided by t. What you are having on the left hand side, we are saying these are functions of x only. What you are having on the right hand side, we are saying these are functions of t only. But in this case, we are saying they are equal. So they can only be equal if they are constants. So we'll call that constant k. So we have x prime prime divided by x is equals to k, and 1 over c multiplied by t prime divided by t is equals to a k. Because we are saying the only way they can be equal is if they are a constant, and that constant we called it a k. So we have those two equations there. I'll start by looking at this equation here. I can just rewrite it, multiply throughout by x. Then we would have x prime prime is equals to k multiplied by x. Then subtract kx from both sides and we would have x prime prime minus kx is equals to 0. What we note there is this equation here is a second order ODE with constant coefficients, because it is of a form which is similar to second order ODEs which you've looked at, a2 multiplied by y prime prime plus a1 multiplied by y prime plus a naught multiplied by y is equals to 0. So we see it is of a form which is similar to this one. And to solve this type of equations, we said we had to find the auxiliary equation a2 multiplied by m squared plus a1 multiplied by m plus a naught is equals to 0. And then the roots of the auxiliary equation determine the general solution that would have. Because we had that if m1 is not equals to m2, then the solution would be c1 multiplied by exponent of m1x plus c2 multiplied by exponent of m2x. If there were real repeated roots, m1 equals to m2, which equals to m, the solution will be c1 plus c2 multiplied by x exponent of mx. If the auxiliary equation had complex conjugate roots, m equals to a plus or minus ib, then the solution is exponent of ax multiplied by c1 sine of bx plus c2 cosine of bx, where the c1 and c2 are constants. So for our equation here, we see that our auxiliary equation is m squared minus k equals to 0. To solve for k, we just put the k on the right hand side so that we have m squared is equals to k, then take square roots on both sides so that we would have m is equals to plus or minus the square root of k. But now in this case, the roots of the auxiliary equation depend on the sign of the constant k. If k is 0, then we would have two distinct roots, plus or minus root k. So our solution will be of this form. So we would have that our x is equals to c1 exponent of root k multiplied by x plus c2 multiplied by exponent of minus root k multiplied by x. And if k is equals to 0, then we would have just one root, m equals to 0. We are having a repeated root where our m is equals to 0, so our solution is of this form. And we are saying our m 0. So if we have m 0, exponent of 0 will give us a 1. So we'd have our x is equals to c1 plus c2 multiplied by x. If k is less than 0, we are saying k less than 0 here to be the square root of a minus k. So if the square root of minus k, that will give us plus or minus I root k, because the square root of a minus 1 will give us the I there. So we'll have that our m would be equals to 0 plus or minus I root k. So our a 0 would have exponent of 0 there, which will give us a 1. So we'll have that our x is equals to c1 multiplied by sine of x multiplied by root k plus c2 cosine of x multiplied by root k. So those are the general solutions for the x. So I now go on and look at this differential equation there. That's a first order ODE. I can just rewrite it by multiplying throughout by c, and we have t prime divided by t is equals to kc. But I can write the t prime there in full. Both t prime is the derivative of t with respect to t. So we have 1 over t multiplied by the derivative of t with respect to t is equals to kc. Then go on and integrate on both sides so that we have the integral of 1 over t with respect to t is equals to the integral of kc with respect to t. K and c are constants there. So when we integrate on the left hand side, we would have ln of the absolute value of t is equals to kct plus a constant of integration, which I'll call c3. And then make t subject to the formula, take exponents on both sides. So we would have t is equals to exponent of kct plus 3. But when you're looking at this part, kct plus c3, by using laws of exponents, that simplifies to exponent of kct multiplied by exponent of c3. Exponent of c3 will give us another constant, so I'll call that constant c4. So our expression becomes t is equals to c4 multiplied by exponent of kct. So we now have the solution for the t. But using the method of separation of variables, we say that the solution for u is equals to x times t. We have our x, we have our t. So our x, we said it depends on the sign of k. So if k is greater than 0, we would have our u is equals to x times t. So we would have this x multiplied by this t, and it will give us u is equals to c1 exponent of root k multiplied by x plus c2 multiplied by exponent of minus root k multiplied by x, then multiplied by c4 exponent of kct. If k is equals to 0, then our solution will be this x multiplied by this t. So we have our u, yes, this one here. And if k is less than 0, we would have our u is equals to x times t. So we are multiplying this x by this t. So we have our u is this one here, c1 sine of x root k plus c2 cosine of x root k multiplied by c4 multiplied by exponent of kct. So we are having 3 different general solutions depending on the sign of the constant k there.